of pass transistor problem, and then we'll shift to the transfer characteristics of a MOS inverter. Just we'll try to learn how the curve is being drawn and what are the characteristics of that particular curve. Certain plotting very important in terms of the DC characteristics of the CMOS inverter which we have designed. And once we complete these two topics, we will be moving on to another. Let me share this. Is it visible?
Yes, sir. There are 3 or 4 NMOS transistors cascaded with one another. Provided as VDD, by the potential to the gate terminal, or rather the potential of the gate terminal, because we are in a pass transistor study. And here we provide a potential also plus VDD. So we have to find out the potential and the output of this particular circuit. What is this potential? The output potential. Yes, anyone? Based on your concept of pass transistor, which we have studied in the second last class, what will be the output potential for this kind of a circuit? So if this transistor T1, T2, T3, and T4. So ultimately we have to find out the potential of the output of the circuit or the drain terminal of the T4 transistor. The drain terminal of the T4 transistor. Yes? Anyone? What will be the output potential? At these ends. Okay, tell me what is the potential at this point? What is the potential at this point? Yes, anyone? What is the potential at the end of T1 transistor? At the drain terminal of T1 transistor, if you provide plus VDD at the source, and of course the gate is connected to a plus VDD. So what is the potential at the end of T1 transistor or at the drain terminal of T1 transistor? Yes? What we learned from the first transistor circuit. Move to that particular class. So we have learned over here? NMOS transistor working as a first transistor. What we have learned from this particular table? If you provide VG equals to plus 5 volts and VS equals to plus 5 volts, what will be the VG potential? Yes, is it visible?
Yes, sir.
So what will be the VG potential if you provide VS equals to plus 5 volts for this NMOS transistor? Yes, tell me, just voluntarily say. Anyone? What will be the drain potential if you provide the source as plus 5 volts for this kind of first transistor? NMOS first transistor.
4.3.
Yes? What it will be zero? VD is 0. That you are finding in this table. That you have learned.
4.3.
When you provide 5 volt in VS, you will find in VD it is 0. That you have learned within that class. The table is also showing what will be the potential of VD. Even if you do not remember, you can see the table and just answer that what will be the potential of VD. What is that? You do not attach a capacitor, mind you. Do not get your concepts wrong. You are not attaching any capacitor, but the load felt in this V terminal is that of a capacitive load. You are not attaching a capacitor as a component. There will be no capacitor connected as a component. Whenever you calculate the potential, whenever you connect the potentiometer probe across this V terminal and ground, it will be providing a capacitive load, and ultimately you will be getting the potential which was last highest potential which was felt over here. That was for 4.3 minus the potential across VD was passed, and that was 4.3 minus. After that, this passing of potential from the source to drain was disrupted due to the non-availability of the channel, because as and when the potential at source terminal increased from 4.3 volts, the channel got cut off because the VGS potential moved below plus 0.7 volts. So as because the VGS potential moved below the threshold potential, this channel was cut off, and after that, any higher potential provided at the source terminal was not passed to the drain terminal. So the last passed highest potential was 4.3 volts, and that will be retained, and you will be receiving that till the end of your calculations of providing certain potential association. Am I clear? So even if in this particular problem, I have not shown the capacitor, but it will be working as a capacitive load in any case. So what will be the potential at this point after T1? VDD minus VTH. Yes or no? So once you provide VDD minus VTH at the source of the T2 transistor, because it is connected in cascade means this and this drain, this and this source. Again this and this drain, this and this source. Again this and this drain and that and this source. This and this drain. Starting in this source. So like this source drain, source drain, source drain, and source drain connect with one another of individual transistors. So VDD minus VTH at the drain end of T1 means that is the potential at the source end of T2. Now, if the source end of T2 gets the potential VDD minus VTH, what will be the potential at drain end of T2? Yes. What will be the potential at this point? What will be the? Tell me. You are getting a source and potential for this T2 transistor as VDD minus VTH. So, what will be the drain end potential? Why? Why? So, this is the VDD. Here you are providing VDD minus VTH for a transistor. Okay. So, what will be the drain end potential? What will be VGS? Tell me. What will be VGS? This is VS. This is VS. This is VG. So, what is VGS? What is VGS? This is VG, VDD. And this VDD minus VTH is VS. So, what is VGS? Yes. VA equals to 5 volts. VB equals to 3 volts. So, what is VAB? What is VAB? So, 5 minus 3. So, this is VG. This is VS. And this is VG. So, what is VGS? So, what is VGS? I am not telling what is VSG. If you have problems in Ohm's law itself, then you just cross check yourself whether you are eligible to get a graduate engineering degree after 6 months or after 1 year. I am telling VGS, not VSG. Why you are subtracting VG from VS? You should subtract VS from VG. So what is VGS? VG is VDD. VS is VDD minus VTH. So what is VTH? Tell me, what is VGS? VG is VDD. VS is VDD minus VTH. So what is the VGS value? VA is 5 volt. VB is 3 volts. So VAB is 5 minus 3 volts. So what is the value?
VTH.
Yes, pardon?
VTH.
VTH. Exactly. So if you are providing the threshold potential at gate to source, will the channel be created or not? You are providing the threshold potential over here. So the channel is created or it is not created? Exactly. So what will be the potential at this end? Channel is created. So you are passing the logic over there, passing the potential over there.
VTH.
Yes? Pardon? One end is VDD minus VTH. What will be the potential at the other end? You You are passing the potential over the other end. So what is the potential value?
ওটাই হবে VDD minus VTH.
VDD minus VTH. Exactly. So what will be the potential at this point? One end of T2 is VDD minus VTH. What is the other end of T2 potential?
Same.
Yes,
Same potential will be there.
same potential. So this will be also VDD minus VTH. Similarly, one end of T3 is VDD minus VTH. What is the potential at other end of T3? VDD minus VTH. Okay, very good. So one end of T4 is VDD minus VTH. What is the other end of T4, or rather the output potential? VDD minus VTH. So even if you club up infinite number of transistors cascaded, in most transistors cascaded, the last output will be VDD minus VTH for this kind of configuration. Is it clear or not? Okay. Now slightly changing the circuit alignment. Slightly changing the circuit alignment. So you want here you have provided plus VDD at the source of T1. The drain of T1 is not cascaded with T2, rather it is providing the gate potential at T2. The source of T2 is again connected with that of plus VDD. There is not have any difference. Again, the drain of T2 is connected as the gate potential of T3. Again, the source of T3 is there. Again, the drain of T3 is connected as the gate potential of T4, whereas the source of T4 remains the same as plus VDD. T4. Now, if this is the output, what will be the output potential? So, what is the output potential for this cell? Tell me. Go through it. Just 2 or 3 times go through it very minor. Every concept to solve this problem has already been done in that particular class, which I am referring to. That is NMOS transistor working as use the concept. So first try to find the potential at every drain terminal. So first try to find the potential at these end. What will be the potential of the drain terminal of T1? Yes. What will be the potential of the drain terminal of T1? If you have the source terminal connected to plus VDD as well as the gate is connected to plus VDD. What will be the potential at the drain terminal of T1? Just we have learned in the previous problem. VDD minus VT.
Okay, so VDD minus VTH. Very good. So that potential is the gate potential of T2. Gate potential of T2 is VDD minus VTH. Find it. It is not VDD. It is VDD minus VTH. And the source potential remains VDD for T2. So what is the drain potential? So you have to find out now the potential at this point. The potential at this point. What will be this potential? If you can tell me this potential correctly, then you can solve the rest of the problem. What will be this potential? For T2 transistor, the gate potential is now reduced from plus VDD to VDD minus VTA, the gate potential, that is VG. Vs is VDD. For T2, we are studying T2. Vs is VDD. So what is VDD? Or rather, what is VGS? What is VGS potential? If the gate potential is VDD minus VTA and the source potential is VDD, then what is the drain potential for T2? Tell me. What will be the drain potential at T2? So consider this T2 transistor as isolation. So if you consider this T2 transistor as isolation and draw this diagram, here the potential is VDT minus VTH. And here you have provided VDD. But this VDD potential, you cannot provide it instantaneously. You are increasing this potential from 0 volt, you start increasing it to VDD. That was our concept of learning the pulse transistor logic. So you are just increasing this potential from 0 volt to plus VDD. So say you are providing 0 volt. So if you provide 0 volt, then this will be VDD minus VTH at gate, and at source it is 0 volt. So what is VGS value? VDD minus VTH. Now VDD is usually plus 5 volt. VTH is usually plus 0.7 volt for silicon made transistor. So here you are providing a gate potential not plus 5 volt, rather plus 4.3 volt. That is the gate potential. So if you provide 0 volt at the source, then what will be the VGS value? What is the VGS value? Yes, what is the VGS value? If you provide gate potential as plus 4.3 volt and source potential as 0 volt, what is the VGS value?
4.3.
4.3 volt, which is greater, 4.3 volt. So channel is created. So as the channel is created, here 0 volt gets reflected over here. Similarly, you start increasing 0 volt to say 2 volt. You have increased it to 2 volt. Now this is 4.3 volt, this is 2 volt. What is VGS value? VG is 4.3 volt, VS is 2 volt. What is VGS value? VG, this is VG. This is VG. VG is 4.3 volt. and VAC is 2 volts. VAC is 2 volts. So what is VGS value? 2.3, 2.3 volt. 2.3 volt is greater than 0.7 volt, right? So channel is created. So what is this value at drain end? What is this potential at the drain end?
VDD.
Yes.
VDD.
What VDD? We haven't received VDD over here. We are increasing it from 0 volt towards VDD. So now it is 2 volt at VS. So what is VD?
It will be
Yes, 2 volt. Further increasing, say now it is 3 volt. If it is 3 volt, what is VGS value? 1.3. So 1.3 volt is greater than 0.7 volt. No problem. It is greater than or equals to 0.7 volt. So channel is created. So what is VD value? 3 volt. Next, 3.5 volt. Increase it to 3.5 volt. Now, what is VGS value? What is VGS value? VG is 4.3 volt. VS is 3.5 volt. What is VGS value? Yes, what is VGS value? You are confused with a simple subtraction event.
1 volt.
VG value is 4.3 volt. VS value is 3.5 volt. What is VGS value? Where you are getting 1 volt? 0.8 volt. That is again greater than or equals to 0.7 volt. So channel created. What is this VD value? Exactly 2.5. Now 2.7 volt. So you are increasing again 0.2 amount of potential at source. 3.7 volt. Now what is
0.6.
0.6? So channel is not created. So what is the tip of point? 3.6 volt. When it is 3.6 volt, what is the VGS value? 0.7 volt. 4.3 minus 3.6. So that will be the last point when the channel is created. Clear? So what will be this potential at the drain end? 3.5. Even in 3.6 channel is created. So what is this potential? 3.6 volt. That will be the last voltage received at the. Further you increase this to 4 volt or 5 volt, it doesn't matter. It doesn't matter. This potential will stop at 3.6 volt. So what is 3.6 basically? VDD minus VTH was already your gate potential. Was already your gate potential of T2 transistor. It was already the gate potential at T2 transistor. What is 3.6 then? It is 5 minus 0.7, that is 4.3 was already the gate potential at T2 transistor. So what is 3.3? 4.3 minus VTH. Is it clear? So the drain terminal will be fixed at 3.6 volts. Whatever be the potential received at the source, whatever higher potential you provide at the source, it doesn't matter. It will just stop at VDD minus VTH was already provided at the gate terminal of T2. So VDD minus VTH was
say 4.3 volts. So it will stop at 3.6 volts. So that is 4.3 minus 0.7. So what is 0.7? VTH. So what is this potential? VDD minus VTH minus VTH. That will stop over here. Tell me, is it clear? So the potential at the drain end of T2 transistor will stop at VDD minus VTH minus VTH. So why VDD minus VTH? Because that is the gate potential. And minus VTH, we have proved that it will be taking another threshold value less over here. Can take another threshold value less at the drain terminal of T2. As because it was fed by not the full biasing potential at gate, rather VDD minus VTH at the gate. So there was already a degraded gate potential being provided for T2. And so this degradation will further increase at the drain terminal. Is it clear? What will be the value of degradation? Further degradation, another amount of VTH, another amount of threshold potential at the drain. Tell me whether it is clear or not. So as because you have provided a degraded gate potential for T2 transistor, this degraded gate potential will create further degradation at the drain end of T2. Whatever be the potential you provide at the source end. So you are providing from 0 volt to plus VDD amount of potential at the source end, but that doesn't matter. Ultimately, here the potential you will receive will quite be controlled by the gate potential of that particular transistor. And already we know that for a fast transistor logic, whatever be the gate potential, amount of threshold potential will be degraded when you receive at the drain. If the gate is itself degraded by VDD minus VTH, then further degradation will occur at the drain end of it. And this amount of degradation will be another amount of VTH potential. So the drain terminal potential at T2 transistor will be VDD minus. So the drain terminal potential will be VDD minus 2 VTH for T2. Similarly for T3, the drain terminal potential will be VDD minus 3 VTH. And we will be receiving at the output a potential white VDD minus 4 VTH. So you further increase in this pattern, you further connect transistors at a certain point of time, you will be getting a very low amount of potential at the output, which will correspond to even not passing the exact logic from the source and to drain. Because still you receive VDD minus 4 VTH if VDD is plus 5 volts and VTH is 0.7 volts, then you receive what? 4 VTH means 2.8 volts. So it is 5 volts minus 2.8 volts equals to 2.2 volts. So already you are receiving a lower logic. So here if you provide plus 5 volts as source, then represents logic 1. But if you receive 2.2 volt at the drain, then that will be in a metastable state. It is neither 0 nor 1. This is a metastable state. The logic will be neither 0 nor 1. Why? Because plus 5 volt 2 plus 3.5 volt plus 5 volt 2 plus 3.5 volt is typically considered as logic 1. And plus 1.5 volt 20 volt is considered as logic 0. Logic 0. So rest of plus 3.5 volt to plus 1.5 volt, we consider that as metastable state. Metastable state, which signifies it is neither at 0 logic nor at 1 logic. So whenever you receive the output at after this kind of 4 degraded output, it will be VDD minus 4 VTH, so it will be approximately equals to 2.2 volts. So it moves to metastable state. So even if you provide logic 1 as the input or source end of input transistor, you do not receive the same logic 1 as the output. So not only the output is degraded, but output is also faulty here. The logic value is also faulty, it is not coming correctly. So here it is VDT minus 3 VTH. 3 VTH means 2.1, so around 2.9 volts. That is also a metastable state. Only in the second one you will be receiving somehow just above the logic transfer. So then if you provide plus 5 volt over here, you receive plus 3.6 volt over here. So this is logic 1 transfer still offers. Rest, even for the third transistor P3, there is a metastable state created at the output. Is this problem clear to you, or is there any confusion? Tell me if there is any confusion, you can clear it. Yes? Everyone? So if you connect the transistors, the first transistors, so here we are using the NMOS transistors in a cascade fashion, you do not have any problem. Only VDD minus VTH amount of degradation takes place at the output. Whatever be the number of transistors cascaded, the output logic value typically doesn't change, because here if you consider plus VDD as logic 1, VDD minus VTH also represents logic 1. So it is not at all degraded. Well, it is degraded, but the logic value is not at all changed. Sorry, it is degraded, but the logic value doesn't change. Here is plus 5 volt is given, plus 4.3 volt is received at the output. How many transistors you may connect in this fashion? But if you change this connectivity to this one, so the second circuit which we have drawn, if you change the connectivity to this pattern, then only after 2 transistors connected, you receive the same logic value. Even if it is degraded, it will be degraded and the degradation will increase exponentially. But then also after 2 transistor, even after 2 transistor, you receive the same logic value. You provide at the source, you receive that at the drain. But further, you connect the third transistor, the fourth transistor, and so on. This degradation takes place to such an extent that even the logic value gets hampered. The proper logic value doesn't pass. And maybe after connecting this fourth transistor, you are not getting proper logic value, rather you are receiving a metastable state. But after you connect the fifth and sixth transistor, you will be getting just the opposite logic value. So whatever the logic value at the source end, just the opposite logic value we receive at the output. P6 transistor, then the potential would have been VDD minus 5 VTH. What is 5 VTH? 5 VTH is 5 into 0.7 volts. That is 3.5 volts. So 5 volt minus 3.5 volt. VDD minus 5 VTH will be 1.5 volt. So 1.5 volt directly corresponds to logic 6. So you are, even if you provide at the source end the logic 1 value of 5 volt, you will be receiving at the drain a logic 0 value of 1.5. So direct degradation takes place even if with the logic, not only with the potential value, but also with the logic. So totally a faulty logic passing occurs connecting in this pattern. Am I clear?
Yes, sir.
So you can get this kind of problems also in your exam. So better make the concepts clear so that in any of the changes in these above two circuits also you may able to solve it. So if your concept is clear, if there is no confusion, then it will be very easy to solve. And this kind of problem hardly takes 5 minutes to solve. Right? So still I am asking if there is any confusion, anyone in the class, you can point it out. You can discuss. I will not move further into this class. Maybe the transfer characteristics curve plot I will be taking up for the next class. Tell me. So this circuit is the most critical one. So just take one transistor, connect it to the other one first, and then calculate using your concept that what will be the VD value. So step by step calculation can give you the correct result. Just make a step by step calculation. Say you considered only T2 and make the gate terminal potential as VDD minus VTH and start moving the source potential from the 0 volt to 5 volt increase and see that what will be the tabular representation for VDD, VD, the drain potential. Then only you can find that at which point of potential the drain potential stops increasing. So that will be the frozen drain potential, sealed drain potential. So that we found as plus 3.5 volt. That we have found as plus 3.5 volt. We have found that potential as 3.5 volt, 3.6 volt, sorry, as plus 3.6 volt. Similarly, if you provide plus 3.6 volt at a gate potential of T3, and the source potential starts increasing from 0 volt to plus 5 volt, what will be the frozen drain potential for T? Find that out using that table. So that will be the way of solving this kind of problem, as we have already done that in this particular problem. Is it clear, all of you?
Clear.
Okay. So thank you for today's class. I will not increase it further. You go through these two problems in your home repeatedly. Repeatedly, you go through this problem and try to analyze it, try to understand that why this result is coming. If required, you can make a group study. Maybe some of you have understood, many of you have not understood in this class. So you can make grouping and study. You can have your own Google Meet yourself and make a group study for you. No problem in that. But clear your concept before we move to the next topic. Is it clear? Okay. Isha, tomorrow I will not be taking any class.
Okay, sir.
Right? I think day after tomorrow I will be taking again another class from 9 o'clock.
Okay, sir.
Okay. Thank you.
Thank